Here's another bandpass filter problem. This one says a bandpass filter has a center frequency of 100 kilohertz. So let me draw the bandpass filter here. Here it is. And it's centered about 100 kilohertz. And it has a bandwidth of 12 kilohertz. So that means 6 off in this direction and 6 off of this direction right here. So this is going to be 106 kilohertz. So that's the critical frequency of the low pass portion of this. And this is going to be 94 kilohertz. Right there. 100 kilohertz minus 6. Distance between the two critical frequencies is 12 kilohertz. Right there. Find the following. Which two frequencies will result in minus 15 dB of attenuation of the input signal? All right, so that puts us right about here. So minus 15 dB. So that's going to happen in two places, this frequency and this frequency. Okay, let's find out what those frequencies are. First, I need to know what is the distance from minus 15 dB to the critical frequency, which we know is minus 3 dB of attenuation. Well, it looks like the delta between minus 15 and 3 is 12 dB. So we have a delta of 12 dB and then minus 12 dB right there. What is the slope of this line right here? It is 20 dB per decade, and it's minus 20 dB per decade over there. So I'm just going to say 20 dB, and then decade is going to come up here like that. And our answer here is going to be in decades. So 12 divided by 20 is 0.6. So the distance from the critical frequency to the spot where it is attenuated by minus 15 dB is 0.6 decades in this case and in this case. So let's figure out what those two frequencies are. Well, I'm going to start here at the high pass critical frequency, which is 94 kilohertz. So 94 kilohertz is where I'm starting, and I'm in decades, so it's times 10, and I'm jumping down in frequency, so it's to the minus, and then how many decades? 0.6. So 94 kilohertz times 10 to the minus 0.6. So that is 23.61 kilohertz. So that's the first frequency that will result in minus 15 dB of attenuation. Let's see what the second frequency is. So that's going to be 106 kilohertz times 10 to the positive 0.6, because now I want to jump up by 0.6 decades. And let's see what we get. 106 kilohertz times 10 to the positive 0.6, and that is giving us 421.99 kilohertz. All right, so that's the two frequencies where the input signal will be attenuated by minus 15 dB. Which two frequencies will result in V out being 70 volts AC if V in is 200 volts AC? Okay, so here's another type of question. All right, so same filter. You know this critical frequency, it's 94 kilohertz. And this one is 106 kilohertz right here. And we want to know which frequencies will result in V out being 70 volts AC if V in is 200 volts AC. So we're feeding 200 volts AC into this bandpass filter, which is right here. And at the output, we are measuring 70 volts AC. So how much attenuation has resulted here? Well, let's see. That's going to be 20 log base 10 V out, which is 70, over V in, which is 200. And let's see how much attenuation we get. 20 log, not natural log, log of 70 divided by 200. That is giving us minus 9.11 dB. All right, so that puts us right about there, minus 9.11, and right about there, minus 9.11, and that's in dB. We know this spot, it's minus 3 dB because that's the critical frequency. Same thing with that one. So we just need to figure out what is the change in dB from here to the spot in question. Well, that is going to be minus 3, minus 6.11. So delta in dB is equal to minus 6.11 dB. What is the slope of this line? It's minus 20 dB per decade. Decade goes up top. And let's see what that frequency or what that distance is in octaves or decades. Can't talk today. So 6.11 divided by 20. So that is 0.305. 0.305 decades right there. All right. Well, if we're at 106 kilohertz and we jump up by 0.305 decades, that puts us at what? 106 kilohertz times 10 to the 0.305. That puts us at 213.94 kilohertz. So that's this frequency right there. And then this frequency is going to be 94 kilohertz times 10 to the minus 0.305 because we're jumping down by 0.305 decades. So it's going to be 94,000 times 10 to the minus 0.305. And that gives us 46.57 kilohertz right there. So that's this frequency. So those are the two frequencies that will result in this 200 volts AC input getting attenuated by minus 9.11, therefore attenuating the 200 volts down to 70 volts AC. Okay, and then they want us to draw a schematic for this bandpass filter using 1K resistors. So here's VN right here. And this is going to be the low pass portion. So there's a passive low pass filter. And this will be the high pass portion. This is not an ideal filter because normally there'd be something there to buffer this and maybe add a little gain. But in this case, we're just dealing with a passive filter. So we're told that this is 1K and this is 1K. This is the low pass filter. This is the high pass filter right here. Well, we know that the critical frequency for the low pass, so critical frequency for the low pass is going to be 1 over 2 pi times R times C. And so the critical frequency for the low pass is 106 kilohertz. And so we're trying to find the value of C. So that means C equals 1 over 2 pi times 106K times 1K. Let's see what that is. 1 divided by, and I always put parentheses around my denominator, times 106 kilohertz times 1K. Okay, so this one is going to be 1.5 nanofarad. And this one right here the critical frequency for the high pass is going to be the same thing, 1 over 2 pi RC. So that means that C2 here is going to be 1 over 2 pi times R times, what is that critical frequency? 94 kilohertz. Okay, let's see what we get. 1 divided by parentheses 2 pi times 1k times 94 kilohertz. That is 1.69 nanofarads. 1.69 nanofarads. And there is the schematic for our makeshift passive bandpass filter. And that concludes this one.